Hi and welcome to Module 7 of our Organic Chemistry unit and our sixth inquiry question, which is on polymers. And our inquiry question is, what are the properties and uses of polymers? And also welcome to the outdoors. I know how much you love hearing the birds, but it's certainly quieter than inside my house at the moment. So what are polymers? Polymers can be natural or synthetic. Many of the natural polymers you might be aware of, things such as silk, wool, hair, DNA, starches, and they're made by living organisms. But then we also have our synthetic polymers, and our synthetic polymers, commonly referred to as plastics, are manufactured either in a lab or inside a factory. Now, many of our synthetic polymers, you're familiar with their regular uses, and they're used because they're cheap, they're versatile, and they're pretty easy to manufacture. So let's look through at our outcome, model and compare the structure, the properties, and the uses. So they're the three things you really need to make sure that you're looking at. We're comparing similarities and differences, the structure, the property, and the uses of addition polymers. That's a specific type of polymerization. We'll also look at another type a bit later of ethylene and its related monomers. For example, polyethylene, polyvinyl chloride, or PVC as it's more commonly known, polystyrene, and polytetrafluoroethylene. Now, we're going to look at some of those. Just again, looking at the question there, it's talking about ethylene. And ethylene, you may also have seen as ethene. It's really important that you use the term that is given in the question, but both of those terms are used interchangeably. So what are the properties and the uses of polymers? So plastics are really amazing, and they come in a variety of different shapes and sizes, colours, with every property you could possibly think of. They're strong, they're flexible, they're elastic, they're hard, they can be brittle, they can be transparent, they can be opaque, and they can be slippery. So how can one thing have so many different properties? And we'll discuss some of those things soon. So as chemists develop new plastics, the whole range of their uses and their properties are also drastically increase. So as you're aware, with our recent news with China not accepting our plastics and so forth anymore, plastics aren't without a cost, and particularly a cost to our environment. One of the things we need to think about is, how are we going to dispose of those wastes once they've been finished with? And another thing is, how are we going to find the source of the raw material that the plastics need to, if the current one runs out? So what are polymers? Polymers are a covalent molecular substance composed of many different monomers joined together, so many thousands of monomers joined together. And what is a monomer then? A monomer is a single unit that is then often ethylene, repeated several thousand times. And polymerization is the name of that process where those small molecules do join together. And the resultant of all of those joining together is called a polymer. So you can see here in our diagram here, just here, this is a single unit. You can see there's two carbons with the two hydrogens off there. You can see that one unit there, and we've got the letter N next to it. N is it's repeated N number of times, similar to some of the things you sometimes see in your mathematics formulas. And you can see in this diagram here, 2 with the hydrogens, then another 2 in the hydrogens. So you can see that that has been repeated several different times in this one, and often it is several thousand times to get our monomer. Now, as mentioned in our initial dot point, there are two different types of polymerization. The first one we're going to look at is an addition polymerization to form those 4 different types of ethylene products. But there's another type that we're going to look at a bit later, and that's condensation polymerization. So like with our addition reactions with our alkenes, in the addition reaction here, there's no loss of the atoms or any molecules. It's simply breaking a double bond to form 2 new bonds. And condensation, again with normal condensation reactions, water is produced in this process, and it's often involving a different number of functional groups. So addition polymerization. Now, looking at our outcomes, it's saying really it's about the structure, the function, and the uses, not so much the process. And we're presuming there that the process so much is not going to be what's being looked at, but simply the structure, the properties, and the uses. So make sure you're focusing on that in your notes. So when we're looking at an addition polymerization reaction, we're looking at the reaction of an alkene, and you can see here in our equation we've got ethene just here, and our bond is breaking, and in doing that the bond breaks, becomes a single bond, and we have got a free bond on either side that it can then join to other ethylene or ethene molecules there. So in the second one here we've got one ethene molecule, another ethene molecule, and they are joining together. Again, the free bonds, because that happens several thousand times. Now, with this here, under some conditions, alkenes can undergo this reaction and they will produce these long chains. Now, it is possible to have side chains off here and branches happening, contributing to the polymer, and that obviously is going to affect their properties a little there as well. So no atoms are lost in this. We just have our monomer that's unsaturated, and then the double bond breaks, and then we're forming a saturated polymer there. So the first one on our list, and the topic of today's video, is our polyethylene. So polyethylene, poly meaning many, and ethylene, or our ethene, many ethylene monomers. So here, our ethene, or our ethylene, is obtained from our crude oil, from the cracking of our crude oil, and it reacts then with itself to produce polyethylene. And that's one example of an addition polymerization reaction. And here several thousand of those ethene monomers are joined together to produce polyethylene. As I said earlier, ethylene and ethene are both accepted terms. Always just use the one that's given to you in the question. As always, using the information in the question to direct your answer there. So again, here you can see one ethene monomer, another ethene monomer, another ethene monomer here. And as it joins together, the double bond has broken, and we've got a segment there of polyethylene. Usually it is represented in this form where we state that we have got the basic backbone and how many times there it has been repeated. So again, that's our structure. Looking at the second part of our dot points are what are their properties and what are their uses. So polyethylene is the most simplest polymer we have got, and it's the most common one that we have. Now, some of its properties there are it is insoluble, which is a good thing because it often contains water and liquids. It's stable, which is also good, and inert in that it doesn't react with a lot of the things around us, which is also good because it's used as a container for many things. It resists attack by chemicals, including acids and bases. Now, if you think of polyethylene as your cling wrap, it can be easily processed as a flexible thin film there. Now, if we look at the structure again, so I'll just go back here. You can have a look here, and you can see it's really long carbon chains. We're talking several thousand, so very long carbon chains, and it's just carbon and hydrogen bonds there. So we've got a lot of dispersion forces happening there, but we've got no other polar bonds, just our dispersion forces. So because of those dispersion forces, it's really tough and it's strong forces between those long chains. Now we can also get some tangling depending if we've got our side branches that are happening there, and we'll look at that in a little while. But because of the different properties that it has, it can be used for so many different things: cling wrap, supermarket bags, garbage bags, milk bottles, but then it can also be used for playground equipment that's really quite tough and durable, as well as irrigation and sewage pipes. So as I said before, there's a couple of different types of polyethylene. We've got our low density polyethylene, sometimes known as LDPE, and then high density polyethylene, which is HDPE. Now, just simply by looking at these two pictures here, you can see the difference. Our low density one has got lots of branching, whereas our high density one doesn't, and it's going to easily stack. So if you imagine that we had the same volume of space, and we were to put both of these products inside there. Obviously we're going to fit more of the high density polyethylene in there. It's going to be able to stack well. Imagine it thinking like stacking chairs together in the back of the hall. When we stack them up in groups, we fit lots and lots of chairs in that same space, whereas if we were to just chuck single chairs in there in any old random fashion, we're not going to fit as many. So our high density, because of that ability to stack well, whereas the low density with its branching chains is going to affect its density there. So we said that we weren't going to focus too much on the process itself, but it may just be helpful just to know there are two catalysts that allow this reaction to occur. And for low density polyethylene, they use an organic peroxide, and for the higher density one, they use the Ziegler-Natta catalyst. And just out of curiosity, and I wouldn't expect that you know it, but maybe be familiar with it, here's our organic peroxide structure and our Ziegler-Natta structure. And that's my dog. So the branching and side chains provide the different properties of the two types of polyethylene. As I've just said, lower density takes up more space, therefore it decreases the density. It's got lots of side chains, but this lots of side chains then also reduces that mechanical strength. But on the other hand, it increases its flexibility, which is really important with things like cling wrap. Now it's got a lower melting point because it only has those dispersion forces, none of those other polar bonds, and it's been brought up recently about using cling wrap on our foods in microwaves and heating them to such high temperatures, and that would probably also be because of that low melting point. So that's something that you might want to look into and perhaps change what you're covering your food with when you're heating those up. Now here's a table just summarising those things there in a really neat table, and you'll find those in your notes. As we talked about with the branching and the non-branching chain, another word that people will often use is ordered, disordered, or amorphous. Think of an amorphous mass. It's got no structure. It's just kind of a bit of a blob there, and that's due to its branched chains. It's got weaker bonding due to the dispersion forces. The chains are further apart because of that branching, whereas with our high density, they're a bit stronger because they're actually closer together and able to hold that tightly. We've got our properties there. As we've already discussed with our lower density. Looking at our higher density there, it tends to be tougher. It's more of our playground equipment and our detergent bottles, those thicker ones. They're tending to be more opaque. Again, they are unreactive, which again is a good thing. And again, because of that stacking together with the type of bonding that it's got, provides it with those uses and those properties that it has. Have a go through the questions that are in your workbook, and we'll move on to our PVC in our next video. See you then.